Unit Operation Classroom. Today we are going to discuss least squared slope estimation. My name is Shekhar Bhattacharjee. Some experimental data are given here in the table and are supposed to be fitted with an equation y is equal to mx. So using the method of least square, we'll discuss what is the method of least square. So this is called y is equal to mx. That means, it just passes to the origin, and these are probably like some experimental data points. So given these experimental data points, what is the best fit of the straight line? Y is equal to mx. That means which is forced to go to the origin. So what will be the value of m that will best represent or best fit these experimental data points? That's basically the crux of the problem. So what we have to do is fit y is equal to mx using the least square method. We'll see why it's called least square. And then we have to do the regression to the origin as it is y is equal to mx, not y is equal to mx plus c is equal to 0. So it goes to the origin. Intercept is constrained or forced to go to 0. So let us say these are my experimental data points here. This is my y, this is my x, and this is a line. This is a predicted line. This is the best fit line. Okay. So if this is the best fit line, so if y is equal to mx, so for each point we can say y is equal to mxi, right? So this is my y predicted. That means which is basically from the equation, right? Which is the best fit equation. We have not yet found out the value of m. So one thing we can say, the residual for each data point, let's say if this is the best fit and this is my experimental data point, so the error, of course, between the experimental data point and the best fit line, we can say this is equal to yi, that means the value, experimental value minus y predicted, which is predicted from this equation. So for each point there will be an error. So for this one, this might be the error, this might be the error. So that's the way these are the errors. Now, the problem is if you add the errors, it might become very nominal, because the positive error might cancel the negative error. So what is the best way to handle this one is to what you do is just, take the square of the error. So square of the errors means whether it's a positive or negative. So there will be always a positive value. So we calculate the square of the errors and we take the summation of all the errors for each point. So this S is equal to, as you can see, this is the error for each data point. We take the square of the errors, which will be of course a positive number, and we take the summation for all the points. So here we have let's say 5 points. Okay. So basically, so what is the value of M? So what will be the value of M for which this sum of the squares of the errors is minimum? So ds over dm, what is value of M? ds over dm is equal to 0. Of course, the second derivative has to be greater than 0 to make it minimum. So this is the equation. So if we take the first derivative, that will be of course 2. That's equal to y minus xi times negative of xy. This one right here. So that has to be equated to equal to 0. Remember, these are the actual experimental data points, and these are from my straight line. So this is the error. Okay. Once this is equated to 0, as you can say, second derivative has to be positive to make it minimum. So we get this as xi x1 minus mxi square. So the value of m can be calculated like this. So how do you do that? Let's see this next slide. So these are the points, xi, these are the experimental data points, These are already given to us. So we calculate xi yi multiply. So xi yi, and when we calculate xi square for each data point, xi square, we calculate that and we take the summation of that. And so m would be just a ratio of these two summations here. So this is equal to 2.5. So here for this one, going to this one will be equal to, the equation will be equal to y is equal to 2.5 times x, or y is equal to 2.5 times xi for each data point. Normally, we put mx plus c. That of course is a slightly different type of equation that resolves. Okay. All right. So how does it look? So these are the given data points right here. And this is the best fit line here, which makes the residual of the errors, square of the errors equal to zero. Not the sum of the errors, residual of the sum of the squares of the errors is equal to zero. And this has fit, this has to force to be go to the origin because we are using equation y is equal to mx. Okay. So that's how it looks like. So this looks like it's a very good fit. Okay, so this type of methodology is the least square regression method is used very extensively in laboratory scale and also in industry. So what are the key lessons concepts here? Determine the model parameter m by minimizing the sum of the squared residuals, that means the error, between experimental data and predicted values. This problem is an example of linear model constrained to origin. So this is the equation what we are using. Typical examples of y is equal to mx might be like laminar pipe flow. Remember, this is the equation for laminar flow. So delta V is directly proportional to Q. For each value of Q, which is X, you experimentally determine what's the value of delta P, which is Y, and you just you get the data point, then use the least square method to get the best value. So what is the use of this method? Because now once you get the equation, for any value of X, you can predict what will be the value of delta P. Next is the first order reaction penalties. Again, this is the typical one that goes to zero. This is for mass transfer, mass flux. This is for the heat flux. For instrument calibration, we know normally we put as output is equal to some kind of a slope multiplied by input. So there's a wide application of this particular problem. Okay. Experimental data can be fitted using linear regressions. We do that quite regularly in laboratories. In practice, measured or experimental data do not usually fall exactly on a straight line because of measurement uncertainty, process fluctuations, and instrument errors. That's why we use the linear regression method. Okay. Answer to this one, M, of course, is 2.5. That's what we got here.